Hello students, today we are going to discuss one more problem that is based on penalty method of boundary condition. Okay, here we have the problem. Using penalty method of handling boundary condition, determine the nodal displacement, stress in each element and support reaction in the bar shown in figure. Due to applied force, P is equal to 100 kilonewton. Here we have the load at the center, that is 100 kilonewton. And here we have two parts. The first part is for steel and second part is copper. For steel, the Young's modulus is 200 GPa. For this copper, the Young's modulus is 100 GPa. Okay, here this is the system. Here it is fixed at both the ends. Okay, here we have the load 100 kilonewton and this is the x direction. Okay, the length of first bar is 800 mm and the second half is 500 mm. So first we'll write the given data, that is Young's modulus for steel. Young's modulus for steel is 200 GPa. So we have to convert this into Newton per mm square. So I will write it as E1, that is for element number 1. That is, after conversion we'll get 2 into 10 raised to 5 Newton per mm square. Okay, similarly for copper we have 100 GPa. So E2 is equal to, after conversion we'll get 1 into 10 raised to 5 Newton per mm square. Okay, here this, the diameter as it indicates, the diameter is 60 mm. For this diameter is 40 mm. For circular section we have the area formula pi by 4 d square. Okay, pi by 4 d square. So before that, here these two are the fixed ends. So here it is node 1, node 2, node 3. At node 1 and node 3 the force will be 0. At this node 2 the force will be 100 into 10 raised to 3 Newton. Here F1 is equal to 0, F2 is equal to 100 into 10 raised to 3 Newton and F3 is equal to 0. Okay, now we'll calculate area, that is for node 1, for element 1, area 1 is equal to pi by 4 d1 square. Okay, so for the first element d is 60, pi by 4 60 whole square, we will get 2827.43 mm square. That is area for the first element. Similarly, area for the second element is pi by 4 d2 square. For the second element diameter is 40, that is pi by 4 40 square. After solving we will get 1256.63 mm square. And we know L1 for the first element, the length is 800 mm and L2 is 500 mm. Okay, so in this problem the first step we have to create FE model. Okay, we'll create the FE model. The first step we have to create FE model, that is finite element model. So first I will draw the line and I will mark 3 nodes. This is node 1, this is node 2, this is node 3. Here the force is F1, the force is F2 and the force is F3, and this is the direction of X. This is F1, this is F2 and this is F3. Here the displacement is Q1, here the displacement is Q2 and here the displacement is Q3. This is element 1, this is element 2, and the length from here to here, for this for element 1, that length is 800 mm and we call it as L1. And similarly for second element L2, that is 500 mm. Okay, this is the FE model. Next we have to write elemental stiffness matrix. Okay, elemental stiffness matrix, that is given by K is equal to AE by LE, 1 minus 1 minus 1 1. Here the E indicates number of element. Okay, here we have two elements, so we have to calculate K1 and K2. So for element 1 K1, area is, as we calculated, area is 2827.43, and Young's modulus for steel is 2 into 10 raised to 5, 2 into 10 raised to 5 divided by length is 800 mm, and 1 minus 1. After solving, we'll get K1 is equal to 10 raised to 5 7.068 minus 7.068 minus 7.068 7.068. Okay, similarly for element 2, K2, that is K2. Okay, K2 is area 1256.63, and Young's modulus is 1 into 10 raised to 5 divided by length is 500. Okay, 1 minus 1 minus 1 1. So after solving, we'll get K2 is equal to 10 raised to 5 inside the bracket 2.513 minus 2.513 minus 2.513 2.513. Here again, this is for element 1 and this is for element 2. So this first row indicates Q1, the second row indicates Q2. The first column is for Q1, second column is for Q2. Again, the first row is here this is for element 2, so here Q2 and Q3. Here this is Q2 and this is Q3. Okay, now I will write global stiffness matrix. Global stiffness matrix, that is K is equal to K1 plus K2. Okay, so as here we have 3 nodes, so 3 displacement values Q1, Q2, Q3. Here we'll get 3 rows and 3 columns, that is K is equal to, the common is 10 raised to 5. Here the first row is related to only Q1, so here this row is for only Q1. I will write 7.068 minus 7.068. Here this is Q1, this is Q2. Here in this Q3 we don't have any Q1 value, so it is 0. And the second one is related to only Q2. Here we have Q2 and here we have Q2. For Q1 we have the value 7.068. For the second one Q2, here we have one value and here we have one more value, so we have to add this and this at the middle, because this column is related to Q2, this row is also related to Q2. After adding, we get 9.581. And this is for Q3, column is related to Q3 and the row is related to Q2, so that is minus 2.513. And this one is Q1 and Q3 row. Here we don't have any Q3 row in Q1, so it is 0. Similarly, we get minus 2.513 and it is 2.513. This is global stiffness matrix. Similarly, we have to write the global nodal displacement vector and global load vector. That is, first I will write global nodal displacement vector Q, which is equal to Q1, Q2, Q3. Similarly, global load vector that is F1, F2, F3. As we discussed, here F1 and F3 0, F2 is 100 into 10 raised to 3. Now I will write the equilibrium condition. Equilibrium condition is given by K, that is global stiffness matrix, and global nodal displacement vector, global load vector. Okay, we have the stiffness matrix 10 raised to 5, 7.068 minus 7.068, 0 minus 7.068, 9.581, 2.513, 0 minus 2.513, 2.513, and into, here it is displacement q1, q2, q3, and the load 0, 100 into 10 raised to 3, 0. Okay, now here we have two types, one is elimination method and one is penalty approach method. Here according to question we have to solve this problem according to penalty approach method. Okay, so we'll apply the boundary condition. Applying boundary condition, so we have to calculate C, that is maximum of Cij, Kij into 10 raised to 4. Here in this matrix we have to search the maximum value, comparatively all 9 values, the middle one, that is q2 row and q2 column, that is 9.581 into 10 raised to 5. Substitute that value here, 9.581 into 10 raised to 5, and in this formula we have 10 raised to 4. So after solving we'll get C value, this 9.581 into 10 raised to 9. Okay, this is C value. We have to add this stiffness value to the this is matrix, stiffness matrix, where we have the fixed end. So in this problem here, this problem is like this. This is the stepped bar which is fixed at both the ends. Here it is q1 and here it is q3. So we have to add this C value to the first element and the last element in this diagonal. Okay, so after adding we'll get that K value, that is stiffness matrix. After adding that C, we'll get 10 raised to 5 outside, 95837 minus 7.068, 0 minus 7.068, 9.581 minus 2.513, 0 minus 2.513, 95837. Okay, now this is the stiffness matrix according to penalty approach method. Now global load vector, global load vector, that is we know F is equal to F1 plus CA1, F2 plus CA2. As per the problem, this is A3. Okay, Q1 and Q3 is 0 because of the fixed point. Here A1 indicates Q1, that is equal to 0, and A3 indicates Q2, that is equal to 0. So this load vector becomes 0, 100 into 10 raised to 3, 0. That is 0 into anything 0, and remaining is F1. F1 is also 0. Here also 0 into anything 0, remaining is F2, that is also 0. Here F2 as it is. Okay, so this is the global load vector. Now I will write the equilibrium condition. After applying the boundary condition, the equilibrium equation becomes first we have to write the stiffness matrix 10 raised to 5, 95837 minus 7.068, 0 7.068 9.581 minus 2.513 0 minus 2.513 95837. Here q1 q2 q3 is equal to 0 10 raised to 5 0. Okay, so we have to solve according to matrix multiplication. Here first row into first column. I will show you how to do matrix multiplication. Okay, so first row first column, 95837 into 10 raised to 5, that is first value. In this column the first value is q1. Okay, similarly that is minus this value into this q2, 7.068 into 10 raised to 5 into q2 plus 0 into anything is 0, and that is equal to 0. And second equation, minus 7.068 into 10 raised to 5 into q1 plus 9.581 into 10 raised to 5 q2 minus 2.513 into 10 raised to 5 q3, that is equal to 10 raised to 5. Last equation, 0 into q1 minus 2.513 into 10 raised to 5 q2 plus 95837 9.95837 into 10 raised to 5 into q3, that is equal to 0. First row into first column, second row into second column, third row into, here we have only one column. First row into first column, second row into first column, third row into first column. After solving this, we'll get q1 is equal to 7.6996 into 10 raised to minus 6 mm, and q2 is equal to 0.1044 mm, and q3 is equal to 2.7377 into 10 raised to minus 6 mm. I will write the same thing in matrix form. So nodal displacement vector is given by q. We have to write q1 q2 q3, 7.6996 into 10 raised to minus 6, 0.1044, 2.7377 into 10 raised to minus 6, and this is in mm. This is the first sub question. Now we have to calculate stress in each element. Okay, so we'll calculate stress in each element. Stress in each element. We know the stress formula, sigma is equal to E by L, 1 minus 1 1, here qi plus 1. If you are taking for element 1, this will be q1 q2, for element 2 this is q2 q3. Now for element 1, sigma 1 is equal to Young's modulus is 2 into 10 raised to 5, length is 800, minus 1 1, q1 is 7.6996 into 10 raised to minus 6, and q2 is 0.1044. First we have to solve this and into minus 1 and this, plus solve this into 1 into this. So after solution we'll get sigma 1 is equal to 26.098 megapascal. Similarly for element 2, sigma 2, Young's modulus is 1 into 10 raised to 5 and length is 500, minus 1 1, q2 q3 we have to write 0.1044, 2.7377 into 10 raised to minus 6. Again this minus 1 into this, plus 1 and this into this. Sigma 2 is equal to minus 20.879 megapascal. Okay, similarly, support reaction, support reaction, we have the formula Ri is equal to minus C Qi minus Ai. Okay, so here we have two fixed ends, so we have to calculate reaction at node 1 and node 2, and also we know that Q1 is equal to Q1 and Q3 is equal to 0, so obviously A1 and A3 is equal to 0. So for reaction at support 1, R1, that is equal to minus C into Q1. What is C value? Minus C value is 9.581 into 10 raised to 9, and Q1 is 7.6996 into 10 raised to minus 6. After solving, we'll get reaction at support 1 minus 73769.86 Newton. Okay, similarly R2 minus C Q3 minus 9.581 into 10 raised to 9, and this is 2.7377 into 10 raised to minus 6. After calculation, R2, this is R3, okay, that is equal to minus 26229.9 Newton. So here we calculated nodal displacement vector, that is nodal displacement, and sigma 1, sigma 2, and R1, R3, that is reaction at the end support. This completes the problem. Okay, next video we'll discuss some more problems. Thank you.